Okay, good morning, everybody. Welcome back. I hope we had a great spring break. Today is March the 27th. We are covering another application of the antiderivative. This one is work. Project number 5 is due, so if it's done, throw it in the folder for me. Project 6 is now officially assigned. Go ahead and grab one from your table. You can put the due date on the top of Project 6 if you wish. It is due April 3rd, which is a week from today. So this coming Monday is when that project is due. And then right after that project is due on Wednesday next week is test number 2. Not too early to start studying for test number 2. Questions on the calendar? Okay, then let's jump in on page 66 with our daily summary. Work is another concept from physics that we can calculate using our slicing technique, which again leads to an integral. Number 0, did you read the article? It slices, it dices, it's copied on the previous couple of pages. It is worth a read. So a couple of preliminary facts from physics. So first, work is equal to force times distance. That's just the definition. And then weight is equal to mass times acceleration. I'm gonna write the word here, force or weight. Force or weight is equal to mass times acceleration, F equals ma. Weight is the force that gravity exerts on an object of a particular mass. All right, so there's some units here for mass and force or weight and work. There's the metric stuff, kilogram, Newton, and joule, and then the English units are there in the middle. So let's start with a non-calculus question number 2. What is the weight of 2 kilograms of iron? The weight of 2 kilograms of iron. So kilograms is a mass, so we've got a 2 kilogram mass, and we want to know how much it weighs here on Earth. So we'll just use our formula up there. Weight is equal to mass times acceleration. Mass is given as 2. Acceleration in metric here on Earth, 9.8. And so we just get 19.6. And the unit for weight in metric, newtons. 19.6 newtons, that's how much the thing weighs. If you were to weigh that thing on the moon, it would be a different weight, right? It would weigh less. Okay, number 3, another non-calculus question. How much work is done lifting 2 kilograms of iron 3 meters off the floor? 2 kilograms of iron 3 meters off the floor. So according to our work formula, work is equal to force times distance. But remember, force is the same thing as weight. So I'm going to write weight times distance. And we just calculated the weight of this 2 kilogram mass. What was the weight? 19.6. And we multiply that by the distance it is traveled. It is traveling 3 meters off the floor. So what do we get there? Thank you. Weight times distance, and work in metric is joules, Newton meters. Okay. So that's how much work we do there. Okay, so now we're ready to do a calculus question. Number 4. A 45-meter rope with a mass of 30 kilograms is dangling over the edge of a cliff, ignoring friction. How much work is needed to pull the rope up to the top of the cliff? So we've got our cliff here, and then we've got this rope that is hanging down, and altogether it is 45 meters. Down to the bottom, and we're going to pull this rope up over the top. Let's take a look at the wrong way to do this. Explain what is wrong with the following solution. So it says work is equal to force times distance. That's our definition. The force is, as we calculated up above, is mass times acceleration, right? 30 kilogram mass, 9.8 acceleration. And then we multiply that force. So I'm just going to underline here. That thing is this thing. Multiply that force by the distance, 45 meters, crunch them all together, 13,230 joules. Why is that not right? Yeah, the mass is changing. Every time you pull a little bit of the rope over the edge of the cliff, the weight of what's left over is less, right? So it gets easier to pull this rope up as more and more of it is pooling beside you on the ground. Yeah? Okay, and so this is going to turn into a calculus question. What we're going to do is slice this rope up into little tiny pieces. Would you guys agree that the particles in the rope at the bottom of this slice don't have to move that much more than the particles of the rope at the top of the slice in order to get to the top of this cliff, especially if I make this thing really small? So we're trying to pick particles that do not have to move very different distances from each other. Okay, so the mass of a section of rope, let's go for it. Okay, so the mass is equal to, so let's give a good name to this distance here, about delta H for that little length. And so then I guess that means I'm calling H the distance that that little slice has to go. Okay, and so to find the mass of that little slice of rope, oh, didn't we do mass calculations our last class? Mass is equal to density times length. Remember this? So we just need to know the density of the rope and multiply it by that length. So we'll write that here, density times length. The density of the rope, how much mass per how much length altogether? What is it? 30 kilograms for every 45 meters. Everyone agree that is the density? I'm putting the units there just so we can make sure that everything cancels out the way it should. Multiply that by the length. What did we call the length of this little segment of rope? Delta H. What are the units for that length? That's meters. And the meters cancel and we get a number of kilograms, which is what we were expecting, right? That's the mass. Okay, so we'll clean this up just a little bit. That becomes 2/3 delta H. Okay, so that is the mass of our little section of rope. Now we're going to find the weight of that little section of rope. So remember, weight is mass times acceleration. We just calculated the mass. It's that 2/3 delta H. Acceleration here. It's again 9.8. Okay, so I'm just going to leave this guy. Am I going to leave this guy? I don't know. 19.6 over 3. It's kind of clunky. Delta H. All right, easiest question on this page. The distance that this little green section of rope is going to move in order to get from where it is to the top of the cliff. H. It's just what we called it. That's how far that little section has to go. And so now we're ready to calculate the work done in moving that section of rope. Work is equal to, what's the definition? Force times distance is good. I'm going to call it weight times distance just because that's what we called it up above. All right, so we're copying the weight, which was blue. 19.6 over 3 delta H. And then we're multiplying that by the distance that the rope is traveling, which is red. That was just H. Note that there's no H squareds in this thing. Delta H and H are two completely different symbols. They don't multiply together and create anything. Okay, so this is the work done in moving one little section of rope. What we want to do is figure out the work done in moving all of the sections of rope. So we're just going to write a Riemann sum and then a limit and then an integral. So let's finish here. Leave a little space because we're going to put a limit in the front of this thing. But summation of terms that look just like that. 19.6 over 3 delta H times H. And remember, our default is I equals 1 up to n. So one thing we need to insert into that expression there is it? Is the I. So remember, it just goes on the variable. So that's saying add up the work done for all of these slices. And this is using n slices, but we want how many slices really? Infinitely many, right? Limit as n goes to infinity. And then we write this guy as an integral. So we've got our big old formula in here, 19.6 over 3. Delta H becomes dH. H sub I changes back to H. And then you just have to look at the picture to find the limits. What is the smallest possible H and what is the biggest possible H? Yeah, smallest possible H is 0 for the particles of rope that are already at the top of the cliff. And the biggest H is the 45 meters for the particles at the bottom. So 0 to 45. So I'm going to type that into the TI-83. Again, I feel ridiculous doing that because it's a linear thing, which we can integrate by hand, but I'm just going to save a moment. Any questions on the setup here? Can I ask why this purple expression here is not exactly right? Like, why is that purple expression just an approximation for the work done for that slice? Where is the approximation happening? Evan? What about the delta H? Mm-hmm. So let's see. Well, so the mass I think is perfect. Like this 2/3 delta H is exactly the right mass. What's changing? The length. Well, so of these two things here, this is open to anybody, the weight or the distance changed. Which one is the approximation? Because one of them is exactly right. One of them is an approximation for the reality. So we agree that the mass is perfect, right? 2/3 delta H is exactly the right mass for that little section of rope, no matter how big or small the delta H is. And then we multiply the mass times the acceleration. So this weight is exactly perfect for that little segment of rope. What's the problem with the H here? That's right. H is here in our picture, but that's going to the top of the slice. And the particles of rope at the bottom of the slice have to go a little bit farther than the particles at the top of the slice. Right? So that's why it's an approximation. But when you use infinitely many slices, like the difference between the top and the bottom of that slice is hardly anything. Okay, he's got a number for us. I think it's larger. How much? 6615. Okay, and let's get some units here. It's work. What are the units for work? Joules. J for joules. Okay, 6615 is good. One quick thing before we move to the next page. Remember we did this the wrong way in the beginning by assuming that like the entire thing by assuming that we had to pull up the entire thing with all of the weight the whole time. What's the relationship between this wrong number 13,230 and the right number, Josh? Less than half? Less than half? Isn't it exactly half? 13,230. Isn't that double the? Yeah, and so there is something going on here. So there is a non-calculus way to answer this question, which I do not want you to do, but I'll share it with you. The particles of the rope that are down here have to go all 45 meters, right? And the particles up here have to go 0 meters. The average particle in the rope has to go how far? Half, right? So if we go to the halfway spot, that's 22 and a half. And I think we could simplify this problem in our minds by taking the entire 45 meters of rope, all of the mass and all of the length, and compressing it to a single point with all of the mass right here at this halfway mark, 22 and a half. And so I think that's why this guy is double, is that it doesn't sort of take into account the fact that you could smush it all, but if you smush it all, it's not going 45 meters, it's only going half. Don't do that. Okay. All right, next page. A water tank in the shape of a right circular cone of height 1 meter and top radius 0.5 meters has a column of water that has a height of 0.5 meters. So all of that is marked in the picture. Find the work that must be done to empty the tank by pumping the water over the top edge. And then there's something there about the density of water. Okay, so we're trying to get all this water out of the top of the tank. Okay, and so first, one thing about like how we're going to get this water out of the top of the tank. If we were to put like a giant hose down in here, and put that hose at the bottom of the tank and then just like start sucking the water out, then all of a sudden we've made all of the water travel like the full meter, because all the water is going to, like the water at the top as the tank empties is going to fall down to the bottom and then have to like go an entire meter. So that's not what we're doing here. We're imagining taking our hose and putting it right up to the top surface of the water and taking those particles of water up, and then moving the hose down just a fraction of an inch and then taking the next particles, so that the water has to travel exactly as far as it is from the top right now. Okay. All right, so let's slice this water. So the water in the tank is the same density everywhere. So the only thing changing here in terms of the work involved is the distance that that water has to travel. So how are we going to slice this so that the water particles have basically the same distance to travel? Horizontally. And so go ahead and draw yourself a horizontal slice. And let's give a name to this thickness here. How about we call it delta H again? And so then maybe, so we got two natural choices here. You can either call H the distance from the top or the distance from the bottom. It makes no difference to me what feels more natural to you guys. One vote for top. Okay. All right, so H can be the distance up to the top of the tank from the current slice. Okay. All right, so we're looking for the volume of a slice of water. So we need the volume of that thing. What kind of a shape is that? The whole thing is a cone, but how about our slice? It's approximately what nice shape? It's approximately a cylinder. It's not perfect because the thing angles in a little bit, but close enough. So volume of a cylinder is pi r squared h. Okay, and so I think this is now a good time to label the radius of our cylinder. So we can say that the radius of the cylinder, the radius of our little slice of water, we're calling it r. So I'm going to leave a blank right here where the radius is going to go in and get squared. But I'm going to change the h. What is the height of our cylinder? Delta h. That's what we're calling the height, right? And so what magic letter needs to appear inside of these parentheses? H. H is the only letter allowed because of that delta H, right? So I need to change the R. I can't leave it as an R squared. So we need to come up with a relationship between the radius of that little slice and the H that we've got up here. So I'm going to draw that same thing, but a two-dimensional cross section going right through the center at the top, all the way through the point at the bottom. And so we got a triangle here. And we're going to start labeling our triangle with exactly the same stuff that we had before. So there's the water level up there, except that's not what I meant. So we need to draw the level of our slice right there. Okay, so according to our picture, R is this distance in here, and H is this distance here, yeah, to there. And then the whole height was 1. And then I think that's all we need. Yeah. Nope, we also need the radius at the top, 0.5. Okay, so what we're going to do is compare the entire triangle to the triangle that is below the red line. Would you guys agree those are similar triangles? And so we get to write down a proportion. So let's write that proportion. So for example, R in the little triangle is to, what's the corresponding side in the bigger triangle? 0.5. And now we're doing, okay, so what I want to do is this purple thing in here. It doesn't have a label yet. How long is that purple thing? That is 1 minus h. We got to have that. Okay, so 1 minus h in the little triangle is 2. What's the corresponding height in the big triangle? 1. So that's our proportion. By choosing to let h be the distance we have yet to travel, that's where we had to put in this 1 minus h. If we had labeled the purple thing here as h, then it would have just been h in this proportion. Okay, so there's our similar triangles set up. Again, we're trying to replace r in the parentheses here, so we're solving this equation for r. So we get multiply both sides by 0.5, and we get that. And so that thing right there can go right in here. Okay, so that's the volume of our cylindrical slice. And now we need to know the mass of that slice. So remember, in the previous problem, mass was density times length. That was the one-dimensional version. What is it here? Density times volume, right? The area would be 2-dimension. Density times volume is the 3-dimensional version. So that's what we're doing here. We calculated the volume. It's right there. So now we can say that the mass of that slice is equal to the density times the volume. Density is given in the parentheses up here at the top. It says 1,000 kilograms per cubic meter. I won't put the units. 1,000 kilograms times the volume we just found up above. Okay, and now we need the weight. What's our formula for weight? Mass times acceleration. We have the mass right there. So I'm going to start to get lazy here just because I want to give you guys lots of time in the activities. So the weight is equal to the mass, which is all of this, times acceleration, which is still 9.8. Next up is the distance that slice of water will be moved. Look at your picture. What should we call that distance? We call it h. Easy. So we called h how far it is. Yeah, h is changing. Yeah. Okay, and then the work. What's the definition for work? Good. So work is equal to weight times distance. Weight is all of this stuff. times the distance, which we said is h. So that big expression that I've hardly written anything down from represents the work done in moving one slice of water, one slab of water from wherever it is up to the top of this cone. To find the work done in moving all the water, you got to add up all the work for each of the little slabs of water. And so that means sigma, which I won't write, and that means the limit, which I won't write, and that means an integral, which I won't write. The previous problem with the rope had like an easy non-calculus way where we just compressed all of the rope to like one single point halfway in the middle. I don't know of any easy way to do this one. Any questions on this? Okay, so why don't you go ahead and jump in on the activity and I will walk around.